Hi, in this video, we want to look at an example of dimension reduction using principal components. All right, so I graded the dimension reduction homework. This is for my summer 2020 data mining 2 class. I looked at your dimension reduction homework, and as a class, we don't understand dimension reduction. That's all right. That's why we take the class. If we knew it already, it would be a waste of tuition and a waste of our time. So what I want to do, I want to go in and I want to try and address some of the issues I saw in the homework, and hopefully we can clear up some difficulties with this. Okay, so, and don't blame yourself. It's on me. I'm the teacher. It's my job to make sure you understand this. If you're frustrated, I'm sorry. I'm putting in this video to try and get things back on track. All right, so dimension reduction. The situation is I have a crap ton of predictor variables. I have a lot of predictor variables. I have more predictor variables than I can deal with. I have too many predictor variables. Okay, so it's blowing my mind. I don't know what to do. I'm overwhelmed. What do I do about it? Okay, so let's go ahead and start looking through this document that I made. R Markdown, beautiful, beautiful R Markdown. All right, so I've got a lot of predictor variables. So there's some inherent problems with having a lot of predictor variables. First and foremost, it makes it so that the predictor variables are kind of like a needle in a haystack. I've got too many things to work with, and I just feel overwhelmed. Also, models that use a lot of predictor variables are harder to interpret. Like one variable models are as easy as this gonna get. Okay, so, first of all, it's hard to wade through all of it. It's hard to interpret it after I build a model if I use all of them. Another issue is that the more variables I have in the model, the more prone I am to overfitting. And that's just an aspect of using, more and more things. I keep on throwing stuff in. Once I surpass the optimal point, things are only gonna go downhill. Okay, so we do not want to have too many predictor variables. Unfortunately, when we're modeling and we started out, we don't know how many is too many. Also, the more predictor variables I have, the more likely I'm going to have one or more of the variables look really, really good when in reality they're really, really crap. And so just from having more and more and more and more predictors, I can just because of fluctuations in the observations, fluctuations in the data, random effects, measurement errors, someone's drunk when they're recording the data, however that comes about, I could end up having something that looks really, really good, and it's actually really, really crap. Okay, and unfortunately, when we do statistics, we don't know what's going on. If we knew what was going on, we wouldn't be using data. So I'm not going to be able to spot these issues a priori going in. So what we have to do, we have to approach modeling from the point of view is, I don't know what's going on. I need to make choices to protect myself from making a bad decision. All right, so what are my options? What can I do about this? So first and foremost, I can manually go through and do variable selection. Like use that correlation and things like that. All right, that'll work. Another way is to select a model structure that does variable selection for me automatically. Okay, that's, such as stepwise selection, forward selection, backwards elimination, stepwise, forward, back, random forest. There's stochastic gradient boosting. There are plenty of techniques that automatically deal with these kind of things. Now, something about this is whenever I use when I use a model that does variable selection, it's going to end up being optimistic fundamentally from the fact that it's building off of the model, or off of the data I have, and generally speaking, since it's picking the best one it can find. Remember, if I'm picking the best in any process I'm doing down the road, I have to remember that anytime I pick the best, I'm expecting a decrease, when I actually have the real results coming out. Why is that? Think of it like this. If I have Rookie of the Year, how well does Rookie of the Year do their second year in a major league sport. All right, they're still good, they're still solid, but they're usually not the best the second year around. Why? Because they achieve such a high level their first go around. It's hard to sustain that. It's hard to keep it going. So, when we look at the best player for 1 year, they're usually not the best player on the second year. It just works out that way. All right, so another option we have is we can do variable clustering, and then what I can do, I can select a representative from each cluster to be in my set of predictor variables. This is a good choice, and one that is a very good one to choose. Another way to go about this is to do variable clustering also, but then I do feature engineering within each cluster to generate a vector that represents each cluster. Okay, so here I put down principal components, but it also could be like an average of all the values, the sum of all the vectors, or the row sums, that is. There's a lot of different ways to go about this. Usually principal components, first principal component from each of your clusters is usually the way to go on this. And then the last way is to do full-blown dimension reduction using principal component analysis, T-distributed stochastic neighbor embedding, non-negative matrix factorization, or really any format that I can get that has a matrix factorization. All matrix factorizations potentially give us a method to do dimension reduction. Now, honestly, the one that is going to be the most useful is going to be singular value decomposition, which corresponds to PCA. But any form of matrix factorization, for those of you who have a stronger linear algebra background, you could go ahead and use the leftmost factor to generate a reduced dimension data set. Okay, so something to think about this is that when I go through and I start doing my interpretation, the ones up here, the ones at the top are going to be the ones that give me easier to interpret models. The ones at the bottom will give me more difficult to interpret. There's advantages and disadvantages for each of these. Like if I want to do manual variable selection, that takes time and it takes a lot of work, but I also develop a better sense of what's going on with my data. And I can use subject matter knowledge to protect myself from issues like overfitting. That's great. Variable selection, this is, like forward, backwards selection techniques. These are very good, and these are well received by a wide range of audiences. Variable clustering, I honestly think that this is a good way to go. That you preserve your original vectors and you get to use them, and you get to keep variables like in your back pocket if there's something surprising in your data that you probably would not have retained if you did selection manually. So there's advantages and disadvantages to all of these, and it's which one's the best is truly a subjective decision. You have to make a choice. Anything in data science ultimately comes down to you having to make a choice. All right, so let's go ahead and run through the example. Here we're using principal component analysis because this is a very well received, well understood method for doing this, and this has a strong mathematical connection for those of us with a stronger matrix algebra background. Okay, so what I'm going to do, I'm going to take the meter data set, and I think I got this from Kaggle or someplace like that. I'll post it. I'll let you know where I got it. And so, I just load the data. It's sheet B. All right, so if I look at the dimension of the original data, I've got 92 observations, 52 predictors. Okay, 92 observations, 52 predictors. If you think about your linear regression class, you know that that is a lot of predictors compared to the number of columns that I have. So I really don't want to be jumping in with a full set of predictors on this one. When I am done with my dimension reduction, I will have 92 rows of data and I will have fewer than 52 columns. So what I want to do, I want to find a set of predictors where I have fewer columns, but the same number of observations. That's what we mean when we mean dimension reduction. I have fewer predictor variables, but I have the same number of observations. And each row in my original data corresponds to the same row in the reduced dimension data set. Okay, so when I'm all done, I need 92 observations, 92 rows. For this problem, the target variable is the health state of the meter. So let's go ahead and take a look at that. I can see that there are 3 different states. We have gas injected, we have healthy, and we have waxing. Waxing is the most common, then gas injected, and healthy is the least common. Well, that's not very good, but let's keep going. All right, now, down the road, I'm gonna want to start doing some plots. When I do my plots, it's a good idea to have to represent a feature of my target variable in my plots. So one thing I want to do is I'm going to go through and I'm going to make a vector that determines the color of each individual point. And this is rather easy since I'm dealing with just 3 different states. So I just take my favorite palette. And for me, my favorite palette is Viridis. This works very well for the colorblind. I take 3 different levels of it. And then all I'm doing here is I'm connecting gas injected, healthy, and waxing to the 3 different colors that I get in the palette. And then on this step, what I'm doing is I'm taking each level of my target variable and I'm making a vector that corresponds, or where the colors correspond to each of those levels. So later on, when I go plotting my points, I understand how each point relates to my target variable. This is going to be very informative down the road. Now it's a little bit more complicated if I have a continuous target variable. There I can either do binning or I have to do a gradient. Honestly, gradient is probably the way to go as long as you don't have skewed data. If I have skewed data, then I want to use like a log transform on my gradient. Also, I have the option of binning. And what you can do, something that will help you is if I just go, hey, let's take the quartiles and bin that way, bin based off the quartiles, and then make a color for each of the 4. Or I can just go up greater than the median, less than the median, and color by that. That way I have a discrete value for coloring. Either way works. You know, if you don't know, start coarse and then improve it progressively until you feel like you understand what's going on. All right, now let's go ahead and let's build our principal component analysis model. All right, so what I'm going to do, I'm going to take all my predictor variables. So on this data set, I don't have any ID numbers. I don't have any stamps of information that are not pertinent to the model. It's just I have one target variable and the rest are predictor variables. So what I'm going to do, I'm going to take my meter data. I'm going to remove my target variable column, and that is this is my collection of predictor variables, just that little old m. All right, now let's actually do principal component analysis with the PRComp function. Okay, remember in R, we have 2 major ways to do principal component analysis. We have PRComp and we have PrinComp. For some reason, R does it in these 2 different ways. PRComp is the way that is numerically more stable, but for some reason, R has it set up, specifically with the psych package, that PrinComp has more features for interpretation. So if you're going to be doing psychometrics down the road, or you're doing something more psychology-based stuff, then you probably want PrinComp. For the rest of the time, numerical stability is more important, so we use PRComp. Okay, that's what I'm using here. All right, so now let's take a look at this. What I want to do is I want to kind of figure out how many principal components do I actually want in this. Okay, in principal component analysis, the first component accounts for the maximum amount of variation in the data set. The second one is perpendicular to the first, and while being perpendicular to the first, it accounts for the maximum amount of variance. The third accounts for the maximum amount of variance while being perpendicular to the first two. The fourth accounts for the maximum amount of variance while being perpendicular to the first three, and so on. And here, so remember variance, if I take the square root, I get a standard deviation. And so down here, I can see how much each principal component accounts for the variation in the data. And you can see it's going downhill as I go from left to right. And you'll notice I have a principal component for every single original column. I originally had 51 predictors. And if I keep on scrolling down, I see that in the full model, I have 51 principal components. Now you'll notice at a certain point, due to rounding, all of the standard deviations are within 0. Now, they're not actually equal to 0. They just round off to be 0. So that tells me not all principal components are useful. There's such little variation in the data set that I do not want them. They are not informative to me. Well, how many do I actually want? Well, what I want to do, I want to look at these values and I want to see where do I have relatively a big drop between numbers. All right, so when I see that I have a big drop, that's where my cutoff is. Now down the road, so if I go through and I was, use my calculator and subtract, I can see where is it like getting, where do I have a big drop in the values? So what I want to do, I want to get the maximum amount of variance accounted for with the fewest number of components possible. I want the maximum amount of variation accounted for with the fewest components possible. Now, what is the correct number? You ask, 10 different statisticians, you can get 10 different answers on this. It's ultimately a subjective decision on what is best. Some people say when the principal components drop below 1, sorry, not principal, when the standard deviation drops below 1, you disregard those. So by that standard, you would go with 1 through 6. Also, if I choose a number, I choose all of the predecessors also in that under the structure of the variance accounting for model of this. So one easy standard to go with is when the standard deviation drops below 1, you stop accounting, you don't account, or you don't take any more in there. So that means that out of all 51 of these, only the first 6 are really useful by that standard. So there's two major criteria for selecting principal components. First one is where I see a big drop between consecutive standard deviations. The second one is when once the standard deviations get less than 1, I no longer include those. They have their advantages and disadvantages. I prefer the drop aspect. Other people prefer the cutoff of 1 aspect because it's a little bit cleaner, easier to understand, easier to spot, less subjective. Whatever, it's up to you. There's really, it's the accuracy of your model ultimately tells you if you made a good choice or not. All right, now when I do principal components, there is an interpretation of each of these, and a biplot can help us figure that out. Here, it's really hard to see what's going on because of what's going on with our markdown, but this is trying to show us how important is each original predictor variable in my first 2 principal components. Now my scree plot is how I do the drop-off method. So here I'm looking down and I can kind of see that, it looks like it's kind of a curve, and then it's kind of flat here. when it flattens out, I probably don't want these. So 1, 2, 3, 4, 5, 6. All right, so you can see that, you know, there is a big drop. There is a big drop, but it's kind of curved. I want to keep on going to the right until I hit diminishing returns. Here I've hit that diminishing returns aspect. Now, where exactly you should pick, I don't know. I would say, looking at this, I would say no more than 6. For this example, I picked 6 because I feel like it is reasonable for this one. If you don't know, go a little bit big, honestly. Go like one big if you don't know. So I feel like 6 is a sufficient number of principal components. You may disagree. You may say 1. You may say 2. It's up to you. It ultimately depends on the data problem you're working on. Okay, so what I've decided that I'm going to go with 6 principal components. That means I have 6 predictor variables. Okay, so this is my new set of predictor variables coming from the principal component model of my original data. I'm just taking the first 6 here. All right, if I look at the dimension, you'll notice I've got 6 columns. And how many rows do I have? I have the same number of rows as my original data. On the homework for my summer 2020 class, for some reason, you guys on the non-negative matrix factorization, you guys went through and chose your topic vectors instead of your basis vectors, which means that you basically just completely screwed it up, which is fine. That's why we take a class. That's why in the examples I built out, I was showing you the dimensions of the factors from NMF. And you can see that I need to have, so the one I want is the one that has the same number of rows as the original data set. Okay, so now, question, do I have good predictors? My goal is not to do principal component analysis. My goal is to make a good prediction. All right, I want in the future to be able to basically have a crystal ball with regard to the health of the sensor. So let's go ahead and let's use pairs to visually understand what's going on with my principal components. All right, so I look through here. So remember, the first principal component is always the one I look at first. That's the most important one is 1, second most important one is 2, then 3, and then so on. Okay, I can see pretty clearly that the yellows are pretty well separated from the purples. Over here, when I get to 1 and 3, I can see that there's a bit of overlap, a little bit of separation on 4, kind of some overlap going when I get to 5, and then 6 has overlap. Okay. And we can go through, and so what I want to do, I want to look at the upper triangle. So this plot and this plot are reflections of each other. They both use first and second principal components. They just use them for different axes. Here, this plot and this plot are reflections of each other. This plot and this plot are reflections of each other. So what I want to do, I want to interpret each of these, then I interpret each of these, and then each of these. Okay, so when I look here, I see that I've got some pretty good separation between the different colored points. All right, that makes me feel good. That makes me feel like I've got good predictor variables. All right, so let's go ahead and zoom in on this one. And it looks like 2 and 3 aren't doing so bad either at separation. Or if I look at just the first and second, you see how I've got all of the teal ones here, all of the yellow ones here, and then all the purple ones here. So I can separate the yellows from the rest by this horizontal line. That means that principal component 2 is by itself sufficient for separating the yellow from the other 2. That is a big deal. That is important. That means I have a good predictor with principal component 2 when I'm looking at the yellow ones. I don't remember which one's the yellow ones, but I know I've got something, I've got some gold in PC2. Now, if I look at PC1, I can see that the teal separates from the other two this way. So if I look at the scatter plot, if I was to draw a line here and I draw a line here, I can make boxes that have only one color point inside each box. That means I have good separation. That means I can build a very, very reliable model off of just these two. So in fact, I don't need 6. I just need the first 2 principal components. So in fact, if I just have a 92 row matrix and a 2-column predictors, then what I have as good of a model as I can possibly get on this training data set. This is exciting. This means I'm very confident in what's going on going forward. Now, this is a small data problem. So one thing about this is that down the road, since I only have a little bit of data, I still need to be cautious because, you know, there just isn't that much data to be working with. So I don't want to get like a crazy precise model off of this. I don't want to do something like neural networks. That's not going to work. Honestly, I think a decision tree would be sufficient for this. Maybe possibly, we could maybe a parallel logistic regression model on this. Yeah, maybe that might work. Now, there is an interpretation of our principal components. Now, this becomes very important if you're going to work in psychometrics, you know, in factor analysis in particular. This is kind of a big deal in psychology. All right, how do I go through and interpret principal components? All right, what I want to do, if I use PR comp, then it is the rotation matrix gives me the principal, that gives me the information about the principal components. Okay, so I'm right now for this example, I'm only going to look at PC1. What we do, we interpret PC1, then we interpret PC2, interpret PC3, and we go along until we feel like the principal components are no longer informative. Okay, so for this data set, I know I would stop before 7 for sure. For this, I might just stop at 1 or 2, depending on how things go. Okay, when you go to interpret principal components, this is my advice. Interpret the largest value first. When I say largest, that's plus or minus. Don't worry, you know, interpret the largest value, then interpret the second largest, the third largest, and so on. So what I've done to kind of help myself focus on what's important, I only took the coefficients in the rotation that are greater than 0.15. Why did I do that? I got rid of everything from negative 0.15 to positive 0.15 because they're small enough that they're not having a huge impact. I still have a lot of stuff to look at because originally, remember, I've got 51 values to interpret if I look at the whole thing. So when I look here, I see that I've got meter performance is the biggest. Then I've got symmetry, signal strength, and then I've got some gains. Okay. Now up here, when I get to the negative 19s, I have meter performance, symmetry, signal strength, cross flow, signal strength. For gains, or well, go on the positive side, I see I've got some gains. Okay. So next, let's go to negative 0.18. I can see that I've got mirror performance, symmetry, signal strength, cross flow, signal strength, signal quality, and then speed of sound. When I get to negative 0.17, I can see that we pick up transit time, the 2 more extreme transit time values. When I get to 0.16, I can see I've got gains and signal quality 1. I'm sorry, that's just straight gains only. down here. And here I've got, you know, all of these and another signal quality. Okay, so how am I interpreting this? What I'm going to do, how I personally interpret this, is that we've got meter performance, symmetry, signal strength, signal quality are the major ones coming into this. All right, so and remember, when I do stuff like this, I'm going to have fluctuating values just because of the randomness of data. Now, is it actually random? We don't know. There could be, like, you know, measurement error and errors in the sensors and you know, transcription errors, stuff like that. But when I look at it, I'm looking for the overall trend. So to me, what I see is that signal strength and signal quality are giving me my negative values. Gains are giving me my positive values. So I'll bet you money if I go through and I start looking at correlation, signal strengths are going to be correlated together, positively correlated. Gains are all going to be positively correlated. And then we'll see that signal strength and gains will be negatively correlated together. And so, but it works out that with their negative correlation, if I switch the sign of one of the vectors, then I can see that they're kind of like pointing in the same direction after I take the negative, the sign switch on there. So overall, I think that signal strength, signal quality, and gain are what really are the most informative predictor variables in the original data set. So if I wanted to go through and start doing some feature engineering with something that's really, really solid, what I could do, I could take the average signal strength, signal quality, I could take the average gain, take the difference between them, and make a new feature that looks like it's going to be easier to interpret, and it'll be, I'll have fewer predictor variables. So one of the uses for this is that this can help guide me towards what is a good idea for building new predictor variables and feature engineering. Another thing that can be helpful is to go ahead and do a bar plot on the rotations. And so what I really want to do, I want to look at which ones are positive, which ones are negative, and which ones give the biggest values. And remember, the biggest values are the ones I focus on first. So like these little nub values, these are the last ones I'm going to look at. Unfortunately, in our markdown, you know, you see how narrow these bars are and how fat the lettering is. I can't really use this, but hopefully this conceptually shows you what's going on. All right, that's all I've got. I hope this clarifies things for you. So the situation when I do dimension reduction, I'm in a situation where I have too many variables to work with. I've got way too many. I can't handle it. I need to reduce down my number of predictors to, one, improve my model, improve computation time, and make it easier to interpret what's going on. Principal components, T-embedded stochastic neighbor embedding, and non-negative matrix factorization are all three major techniques to use. Principal component analysis is usually the best one to use if I'm going to be using a matrix algebra model. The T-distributed stochastic neighbor embedding is a good one in general, but it takes a long time to compute, and non-negative matrix factorization is a good technique if I have non-negative entries on my data set. So like when I have counts, specifically when I'm doing bag of words analysis, and a nice byproduct of that is when I get topic analysis for free. Okay, I hope you enjoy this video. I hope you're staying safe. Take care and goodbye.